In this video here, we're going to look at an introduction to something called the magnetic field. So by way of introduction, we're going to sort of throw a word out there, which is electromagnetic. Now maybe you've heard this word before in terms of electromagnetic radiation or electromagnetic waves. It turns out that the wireless world we live in with cell phones and routers and things like that all work on the principles of electromagnetic radiation or electromagnetic waves. Kind of a scary word, but at least in a physics course it has a meaning and it really isn't that scary. We try to understand these things. In the first half of the word here, the word electro here, that refers to the electric field and all the stuff that we've been doing sort of the first half of this video series here. And the word magnetic here, that's going to refer to the new stuff we're doing, or this magnetic field. It has a symbol B like that. So there is sort of a coming together or an eventual marriage of the electric stuff and the magnetic stuff, or the electro and the magnetic, that then has to do with electromagnetic phenomena, which will probably be covered in some later videos and stuff. So anyway, just by way of analogy here, what are some of the things we know about this E world over here? Well, you know the symbol is E, and you know you have the equation of electric field for a point charge, kq over r squared. There was a force law that we knew about, QE like that. The words volts came up for the first time. This sort of happened when we started moving charges around in fields. You know that matter carries sort of a fundamental charge Q like that. The word Coulomb came up for the unit of that charge. And probably the thing that we grasp onto the most is the electric field, say, created by a positive charge, which are these electric field lines which sort of go out in all directions like that, away from the positive charge. And the negative charge sits here and also fills all of space around it with electric field lines, but its electric field lines go towards it like that. They go in towards it like that. So we sort of have that going on. And so by way of introduction to the magnetic field, I really want to encourage you now just to forget all this, okay? They really are two separate halves of a more unified theory, and in fact there really is no relationship between any of this stuff that you learned and the magnetic field. It's just that different. Okay? There's going to be some analogies, there's going to be some coincidences, and there's going to be some things that sound the same, but they're just not. So you should just categorize those away right now. We're done with them for now. And let's move on to something else, which is the magnetic field. So the first thing you have is, of course, you have this new symbol, which is B, not E, and the unit of this here is in Tesla. So yeah, that's where the electric car company's name came from. The magnetic field unit is Tesla here. You can contrast that with the electric field. Remember, the volt per meter or Newton per Coulomb, where the unit's over there. So we have a new unit going on now. Where the electric field did have to do with charges here, and these positive and negative charges right here, the magnetic field also has to do with charges, but they have to be moving. So charge has to be moving, and when you have moving charges, that'll generate this so-called B field, or magnetic field as it's called there. Okay? So likewise in the electric world, we do have those positive and negative charges right there. And in the magnetic sense here, we're going to have, as you may know, north and south poles of a magnet. Okay, we'll have north and south. Again, purely coincidental like this. There's no relation between them, that you sort of have these opposites, the positive, negative, and the north and the south. There's just nothing, no relation between them. So as you may know, you can have a bar magnet like that with a north pole and a south pole. And one of the things you can do to the magnets is you go, well, what do you mean there's no relation between positive and negative? I bet if I break this magnet in half, I can get just a north pole, which is like a positive, and just a negative, which is like a south. But it turns out you can't do that. So if you break a magnet like this, this will be north and south, and that'll be north and south. It'll just quickly reorder itself. From one big magnet, you'll just get two smaller magnets. So it turns out that isolating a north or just a south pole all by itself, the way a positive or negative might be isolated, in theory or in principle is possible, but it's never been done before. It's never been observed. These so-called magnetic monopoles, mono meaning one, magnetic monopoles, have never been seen before. So maybe someday, maybe you'll discover it. Okay, and so also, like these field lines, which we're used to from electric fields coming out of positive and into negatives and that sort of thing, turns out magnets also have field lines, but they're B field lines now. And sort of the rule is that these magnetic field lines will come out of the north pole and go into the south pole, and they curve around like that. Magnetic field lines sort of always have to be continuous like this. They always have to have a origin and a destination, and they're going to loop around like this. We see a lot of systems where it behaves like that. And so you do have sort of another little idea here that if you have a north pole right here of a magnet, magnetic field lines will come out of it, all kinds of shapes. And if you have a south pole of a magnet like this, then the magnetic field lines will go into it like that. Now, I'm not saying anyone isolated these two poles here like that. I'm just saying this is just a cutaway view of a magnet. The south pole's over here, and if there's a south pole here, there's going to be a north pole over there. Just a little cutaway view. So that's sort of what magnets look like. Those are the bar magnets that you were probably used to and have played with before in school and that sort of thing. It turns out the Earth is a big magnet. So if we have the big globe like this, and here's the good old Earth sitting here. The Earth, of course, has a north pole, a geographic north pole, and a geographic south pole. So this is up at the north pole, that's at the south pole right there. And it turns out the Earth has magnetic field lines. And the way it works with the Earth is the magnetic field lines look like this. They look something like this. They look just almost like a bar magnet. These are B field lines here, so we label these B like that. And what we know about the Earth is that the magnetic field lines go into the geographic north pole and come out of the geographic south pole like that. They come out of the south pole like that. Again, these aren't poles of magnets. These are the geographic poles, the way we've assigned them living here on Earth. So what that must mean then is that the Earth inside behaves like as if there's a big bar magnet implanted in this. And if you can guess where the poles are, the magnetic north is going to be down here, and the magnetic south is going to be up here. So the Earth behaves like a magnet where the magnetic south is near the geographic north, and the magnetic north is near the geographic south. That's the way the Earth behaves. So these are its B field lines. And there's all sorts of ramifications for these B field lines. They protect us from high energy particles coming in from outer space. And if you're familiar with the northern lights and so on, that happens when something like a positive charge like this, or a negative or something, comes in from outer space and sort of gets hung up in these magnetic field lines. It turns out they start corkscrewing around like this, and these corkscrews here, when these charged particles make these corkscrews, that's where the light comes from, because the charged particles are being accelerated in there. So that's sort of some ideas here about what we're getting into with this introduction to magnetism here. A few more things here. For instance, we don't want to go too simple, but it's just sort of a bit of a conundrum for us here, because this interaction is so well observed here. If you have a magnet like this with a north and a south, and say you bought it near a paperclip, or anything metal for that matter. And by metal I mean something with some iron in it, some good old Fe iron in it from the periodic chart. If we bring it near that, you know that even with a good spacing between us, if the magnet is strong enough, the paperclip will actually jump out of its rest position, overcome friction, and even jump in the air, and it'll just jump on there and cling to the magnet. So this thing will kind of, without too much prompting, to get close enough, just go over there and stick to the magnet right there. But it turns out that as simple and familiar as this phenomena is right here, the nature of this force in here, of exactly what is it actually that tugs on this paperclip to bring it to the magnet, is pretty difficult to understand. We'll give you some hints on it in a later video where we talk about magnetism and matter, but for now, yeah, it's pretty tough. That really obvious interaction that everyone has seen and everyone has played around with is pretty darn hard to understand. And so likewise, of course, that means if you go in your kitchen and you have your refrigerator sitting there. This is an American style refrigerator, very big, as we know. And you look at your refrigerator, well, you have some magnets on it. You might have some pictures on there like that. So what that also means is this magnet here that somehow sticks to the refrigerator. This also, very difficult to explain. Same phenomena as the magnet up here attracting the paperclip, but all these things we have in our refrigerator, why does it stick? Is there something adhesive, or is it one side of the magnet or the other? It's a difficult thing to describe, but again, we'll try to hit it when we talk about our video a bit later on magnetism and matter. So just a couple more things just to wrap it up here. Well, the electric field, when we're talking about electric field stuff, we always had this constant epsilon naught. Well, the magnet field has a new constant, which is mu naught, and the value of it is 4 pi times 10 to the minus 7 here. And you can sort of look the units up in the front cover of our book there, but it's definitely a new constant that we're going to have floating around when we talk about our magnetism here. And what else do we have? I guess lastly then, let me just wrap up the video here with something that has to do with the idea that magnetic fields are produced by moving charges once again. So we said charges have to move. Okay. That's sort of a big idea here. They're not produced just by charge alone, but moving charges. And so what we have here is, like, when you think about it from some of our electric stuff, what was the ultimate in moving charges? Well, it was a wire like this with a current in it. I like this. So a wire. So, because of course, what is a current? It's a bunch of electrons moving through a wire here because of an electric field that's inside of the wire. So if these are moving charges, are you trying to tell me that there's a magnetic field that exists in the space around the wire? And the answer to that is yes, there is. In fact, for a wire like this, with a current moving to the right like that, there's going to be magnetic fields in this direction right here. When I draw dots like this, is a new notation that we have to get used to here, because magnetic fields have a lot of three-dimensional phenomena. In other words, things that we're going to be drawing and talking about will come out of the plane of this whiteboard, so you have to get used to the 3D a bit. And so what I'm drawing here is the head of an arrow. So if an arrow looks like this, the tip here, if it was coming at you, would look just like that, and that's sort of what I've drawn here. And I could draw all these little circles around, but I won't, but these are tips of arrows coming at you. And of course, if the arrow was going away from you, the tail here would look like little X's like that. So sometimes you see these little dots and X's, but it means an arrow is either coming towards you or away from you. Hey, I didn't invent it, but best we can do with a piece of paper. And so what will happen then is if the magnetic field is coming towards you on the top of the wire, it'll be going away from you on the bottom of the wire like that. And so yes, if you run current through a wire, this is what the B field is going to look like in the region around the wires. Now what it'll do to a paperclip or another wire or whatever is what we'll study in the upcoming videos and things like that, but this is exactly what happens here to a wire like that. And so what we've noticed then is that if we draw the wire going straight on like this, like suppose we sort of looked at the wire from this perspective right here. Okay, we're going to look at the wire head on like that. We'll see the current coming at us like that. Okay, so this is what the wire would look like. So here's another example of that three-dimensional drawing I have to. Here's a wire, and that dot means the current's coming right at us like this, right at us. So what will happen is, as we'll discover with a right-hand rule, it turns out that the magnetic field sort of does this kind of thing around the wire. These arrows here are the direction of the magnetic field. And on the diagonals, they just sort of follow each other like this and like this and like this. They sort of follow each other. So if you filled in all of the gaps in there, what you would sort of map out is a magnetic field line where the vectors are all along a circle like this. So this is how you would draw the magnetic field outside of a circle. Now, of course, the magnetic field gets weaker as you move out. So if I drew this arrow this large away from the wire, if I got farther away from the wire, I'd probably have to draw a little arrow like that, even farther, even smaller. And if I got really close, maybe the arrows would be really big. So the magnetic field does get weaker as you move away from this source of moving charges. And that's the nature of the game here. And so this will be sort of but these arrows will all collect in a circle like that. And these arrows would be in a circle, and these arrows would be in a circle too. And that's sort of what you get for the magnetic field outside of a wire. So then the last thing is maybe something that you heard about in the news or something like that, is where if you have power lines. So here's a big power line like this. Here's a big power line like this. Those big towers that we see going across our landscape carrying across our badly desired electricity. And they usually have a bunch of wires on them, maybe at least 2 or something like that. They're all kind of connected here and off they go. So the issue then is, well, there's some wires like that, and wires are the sort of the ultimate source of moving charges, I suppose. And suppose that the land near the power lines are cheap because they're so ugly, and they decide to build a bunch of houses in there. See this quite a bit, houses by power lines. So the question is, well, gee, if there's current in these wires, and we just said that current is the source of moving charges, and moving charges make magnetic fields, does that mean these houses are immersed in a magnetic field? The answer is yes, they are. So, for instance, if the current was going this way, the magnetic field, because of the current, would actually be piercing the houses in a manner like this. But not just the houses, of course, all space around there. So the real question then is, if you have this magnetic field in the wires, we'll know 2 things that we'll work on. Is that the magnetic field is sort of proportional to the current. So the more current you have in the wires, the higher the magnetic field is going to be. But the magnetic field is also inversely proportional to the distance from the wire. Something like that, 1 over the distance in here. So whatever the current will be in here, who even knows what that number is? I'm sure it's something we can look up. I think the voltages anyway, which are different than currents, can be up as high as 15, 20, 80,000 volts, something like that. But then what you're concerned about is this distance in here, this distance r. What is it? Because the magnetic field drops off linearly with that distance in there. So do they build houses far enough away, or are they still too close? Or one thing you might ask is, if this is the B field due to the wire here, how does it compare with the B field due to the Earth? That's maybe something we'd like to know if you're going to assess the dangers or something. So anyway, those are just the facts, and these are some facts to help you make informed decisions about them, proportional to I, 1 over R, and probably the most natural comparison is how does it compare with the Earth's magnetic field. And so one more thing about those magnetic fields again, probably should have mentioned this when I was talking about wires more like that, but suppose I have that wire like that, and the current's coming out. Well, let's turn the current off just for a second. So let's have a wire where there's no current in it. But suppose everywhere around the wire I put a bunch of compasses around the wire. So say I had a compass this one was pointing this way and like that way and like this. I guess they should all point north or something like that. Let's just suppose that for some reason they're pointing all different directions. These are compasses here. And you can imagine putting the compasses then in their little plastic cases like this. So the question is, if they look like this now, sort of in all different directions, because maybe they're not great compasses, or maybe there's some weird magnetic field environment or something like that, what happens now when you turn the current on? So when the current is suddenly turned on in the wire like that, if you get a nice strong current in there, it turns out the compasses are all going to align themselves like this. So the compass sitting here, its arrow is going to go this way. The compass sitting here, arrow is going to go down. The compass sitting here, arrow is going to go that way. And the compass sitting here, the arrow is going to go up like that. And the compass up here, like this compass line is going to go from upper right like that all the way over to the upper left. This one's going to sort of go down like this. So you'll see all these compass needles sort of align themselves with the magnetic field. So what we're saying is that if you cover this stuff, oftentimes you'll see a compass come up because they're wonderful indicators of a B field. They're used to tell you the presence of them and the direction of them, because these needles will abruptly start moving if some bizarre magnetic field environment is around them. So if you go from a wire with no current, suddenly turn a current on, all these compass needles are going to abruptly align themselves. So that's another thing that could be brought into that house under the power line thing. You can sort of hold the compass there and see if it reads any different than the compass would very far from the wires, and to get a comparison with the Earth's magnetic field. Anyway, so there's a little introduction to the magnetic field.